Hello and welcome back to another lecture from organic chemistry. Whenever you are trying to prepare a sample for NMR, you need to be sure that your sample is 100% soluble. And that means like you do not deal with any heterogeneous mixture. It has to be 100% soluble, so completely homogeneous. And the next thing is when we put the sample, like the NMR actual tube, inside the NMR, and that tube all the time is spinning really fast around itself. Okay, what's the reason for having homogeneous solution and also spinning the NMR tube? The reason for it, we want to be sure that the magnetic field around this tube, okay, that is carrying our sample is homogeneous. From any side we look to it, the magnetic field is different. The difference should not come from the fact that we have a different strength of magnetic field around the sample. No, it should come from attraction of the magnetic field of the sample with external field. Okay, now in some cases, molecule, whenever it gets exposed to magnetic field, it can create, it can create magnetic field, and that magnetic field it can actually attract, and it can increase or decrease the external field. But it will do it in a way that in one side of the molecule we have a higher magnetic field than another side. It's not because of our NMR machine. No, the molecule created the created magnetic field, and that's gonna technically mess with like the fact that the magnetic field around the molecule is not going to be homogeneous anymore. Okay, let's go after that one and practice some example. Okay, so there's a peak around 7 ppm, and that's for aromatic protons. So anytime you see a signal around 7, be sure that you are dealing with a phenyl ring. Okay. And I want to talk about the anisotropic effect and what's exactly this effect. So let's assume we have a benzene molecule and we applied the external magnetic field. And because we have a pi system there, that pi system, the electrons of pi system, very soon they start moving. And they can actually start moving inside that ring. And that's going to create a magnetic field. Okay, so the magnetic field, we can draw it this way. Now, I'm going to say the magnetic field here is going up, and that one is coming down. And I'm going to call this magnetic field of the pi electrons. Okay. Now, let's talk about these hydrogen atoms that are attached to the phenyl ring. They feel the external magnetic field. So I'm going to say the magnetic field that these hydrogen atoms will sense, it will be equal to the external magnetic field that machine is applying. Also, the pi system created a magnetic field that is aligned with external field. Okay, it's the same direction with the external field. And we said this is the magnetic field of the pi system. So we are adding new, or like a new term or a higher amount, okay, extra amount to the magnetic field of the machine. So what's going to happen with the effective magnetic field? The effective magnetic field, it will go up. That means the gap between two states, it will be bigger and bigger. I guess it gets big, and so that means if this one is the alpha and that one is the beta, delta E, it will go up. You need to apply higher frequency, radio frequency number to get actually resonance, and we're going to see this one in higher ppm number or higher chemical shifts. How about alkene? Alkene system, again, it has a pi system, it has a pi bond or pi system, and it can have the same, it can actually generate the same magnetic field. So we will have, let's say, forgive me, I can actually go with this. So we're going to say we have a magnetic field that is traveling in this direction. And again, same thing here. If you pick any of these hydrogen atoms, okay, as you see, they are going to sense external magnetic field plus the field that the pi bonds are going to apply. And as you see, the magnetic field is going up, is aligned with external field. And so I'm going to call this one B pi. and B pi will be added to B0. So we're going to get higher chemical shift. And as you see, the chemical shift for those alkene hydrogen is hanging between 5 to 7. While for CH3, we expect this one to be around 0.9 or say like 1.9. And say CH2, it will be 1, maybe 1.2, 1.5. And CH, it can go to 1.7. But for alkene, went up to 5 to 7. It's not just because we have sp2 hybridization, so there's more induction effect. No, there is anisotropic effect also involved. And do I have the same effect for aldehyde? Let's double check that one. So I'm gonna draw a circle here, and same thing there. Okay, and I'm gonna say I have a magnetic field is moving in this direction. So the hydrogen atom, the aldehyde hydrogen, the hydrogen atom that attached to carbonyl group is going to fill new magnetic field, which is going to be the pi because of the pi system. And so again, effective magnetic field, it will be B0 plus B of the pi system. And so now we have two technical factors are involved, and they are causing the magnetic field, the chemical shift to go even higher number. One, okay, we replace carbon by oxygen. Oxygen has higher electronegativity than carbon. So I expect the chemical shift to go up because of oxygen. And then the second thing is we have a pi system that can create a magnetic field, and it will de-shield the hydrogen atom, and that's going to end to higher ppm number. Okay, how about the alkyne? Okay, alkyne molecule is completely linear. Okay, and when you put it in a magnetic field, the axis of the carbon-carbon bond, it will be aligned with the magnetic field. Okay, and you can have a circulation of, technically, you can have the pi system start, like in circulating whenever you apply the magnetic field, and it's going to actually circulate in this, this direction. And this one, very soon, is going to create a magnetic field for us, and the magnetic field, I can draw it this way. And and the magnetic field is coming, like you can draw it this way. Magnetic field this time is facing actually down. Okay, and why facing down? Because look to the hydrogen atoms. Hydrogen atoms are there. Okay, so the magnetic field that the hydrogen atom will feel, it will be equal to, forgive me, it will be equal, if I call this one B pi, effective magnetic field for the hydrogen atom is going to be B0 minus B of the pi system. Okay, so the effective magnetic field is going down instead of going up. Okay, look to the previous one. Always we added the magnetic field of the pi system. Now I'm subtracting it from the external one. So what does it mean? It means the magnetic field that the hydrogen atom will feel, it will be smaller. So the gap between alpha spin state and the beta spin state, it will be a small one. And because it's small one, delta E that we need to get resonance will go down. And that's gonna mean smaller frequency number, okay, or less, less energy. So we're gonna see this one in lower ppm. Okay, or how about this? We say we're going to see it close to 0, okay, and on the right side. And so we're going to see this one in ob filled area. Okay. Now, what will happen? We have a system that has a pi system, and it has hydrogen, okay, inside and outside and inside the molecule, and those hydrogen, they can fill, like technically two different magnetic fields. In this case, we have a pi system. We can have a circulation of a pi system, and that's going to create a magnetic field. Let's draw the magnetic field. So I'm going to say I have a magnetic field. And let's say the magnetic field is moving this direction. Now, highlight the outer atoms. For example, those atoms. Those atoms, they're going to fill the external magnetic field, which is pointing up. And that's going to be B0. So I'm going to say the effective magnetic field for outer hydrogen atom is going to be B0. What else? The pi system creates a magnetic field that's aligned with external field. So we're going to add that magnetic field to the external. Okay, so the effective magnetic field is going to go up. That means delta E, the gap between alpha and beta, it will go up. And that's going to give us a bigger chemical shift, or we say we were going to see it in down fill area. How about the one that they are inside? Okay, let's highlight those hydrogen atom. Okay, now track track those actually. Yeah, I should say maybe not signal, like the magnetic field vectors. Vectors are pointing down, and they are going out here. Okay, and so the internal hydrogens are sensing magnetic field from the pi system and opposite of external field. So the effective magnetic field for them is going to be B0 minus B of the pi system. The output of this, we say those electrons will be shielded, and because they are shielded, the gap between alpha and beta will go down. So the chemical shift will be lower number, and you're going to see it in down the high field area. Okay, so as the chemical when the chemical shift goes up, okay, that means the effective nuclear charge is getting bigger. Effective magnetic field is getting bigger and bigger, and that's technically is going to de-shield the hydrogen and the nucleus. And so the nucleus, it can sense stronger magnetic field. So the gap is going to be bigger and bigger between them, and that means you need to apply higher amount of energy to get a signal or resonance. Okay, there's a table here, like in I think next slide, and that I highly encourage you to make yourself familiar with these two slides, because they're going to help you a lot to technically interpret the NMR spectrum. You really need to know this table, or maybe this one. And during the exam, I'm going to give you, actually data like a chemical shift for most common functional groups. So you will have those, but I highly encourage you to make yourself familiar, so then you don't need really to refer to tables to interpret the signal that you see. And I'm going to stop the lecture here, and thank you very much.